Good day, ladies and gentlemen, and welcome to our next visual lecture around the face rule. So, as you can recall from the previous lecture, I think we spoke extensively with the number of component as well as the number of faces. Because the other thing that we did, I think we also did some calculation in terms of how can you calculate the number of component, and also how can we calculate the number of faces. Okay, talking about the faces, let us not forget that we can have at most three faces. So those faces, we can have the solid state or the solid phase, we can have the liquid phase, and we can also have the gaseous phase. Only three phases. Okay, for the component, we said that the component are the number of chemically independent constituent in our system. So in other words, so if you are given a reaction or if you are given an equation, so you have to look in terms of your equation or your reaction and calculate the number of ions or the molecules that are present. I think it's very straightforward in terms of how to calculate the number of component. But before we talk about the phase rule, there are certain factors that we also have to take them into consideration. Okay, factors such as temperature, and factors such as pressure, and factors such as temperature. So if I can make an example with water, we know that maybe at lower temperature, maybe 0 degrees Celsius, water can be found in terms of the solid phase or the solid state. But when we increase the temperature of water, maybe from 0 to 100 degrees Celsius, the very same solid state, it will be converted into the liquid phase. So from that example, I think you can see that the temperature have a huge role that is playing as far as the phases are concerned. So certain of these factors, they can be varied independent. So when we talk about the phase rule, so we are basically talking about the relationship between the number of component as well as the number of phases in the system. So this relationship, it is given by what we call the degree of freedom of the system or the variance of the system. So by definition, the degree of freedom of the system is given as the number of variables which can be varied independently without changing the number of phases. Or the degree of freedom or the variance of the system is related to the number of components and the number of phases. So the phase rule is given as F is equals to C minus P plus 2. So if I can say that state the phase rule, if you state the phase rule, you are simply going to say F is equals to C minus P plus 2. Or you can say that the number of degree of freedom or variance of the system is related to the number of components C and the number of phases. So like I said from the previous slide, so the phase rule is given as F is equals to C minus P plus 2. So as I said, so for this rule is the relationship between the number of components as well as the number of phases. So they are related with the variance. So the variance, even from the previous slide, so by definition is the number of intensive variables that can be changed independently without disturbing the number of phases in the equilibrium. So C, which is the component, is the chemically independent constituents of a system, which is the minimum number of type of independent species. So those species, they can be in ionic form or they can be in molecular form that are necessarily to define the composition of all phases present in the system. So the other term that is not included in this system is the P, which represent the phases. As we know that we can have 3 different phases depending on the system. So the good thing around the P, so when we are given the reaction, always, I think in our reaction, will show that this piece is whether is in gaseous form, liquid form, or is it in the solid form. Okay, moving forward, good people. Okay, for the phase rule, we know that, or we have said that F is equals to C minus P plus 2. Okay, for this phase rule, there are two component systems that we are going to have a look at. The first one is whereby we have one component system. The second one, we are going to look at 2 component system. So for this lecture, I want us to focus only on one component system. So for one component system, it means you only have maybe one ion or one molecule. Maybe we can make an example of water. In other words, in our system, we just have water. We don't have water plus something. Or maybe we can have carbon dioxide, and it's just carbon dioxide. So those systems, they're just known as one component system. So for one component system, F, it is equals to 3 minus P. So why are we saying it's 3 minus P? So from our equation, as you can see that where it was the capital letter C, it has been substituted by 1. So if you say 1 plus 2, we're going to find 3. So in other ways that for one component system, F is equals to 3 minus P. So when only one phase is present, it means that F will be equals to 2, and both the pressure and the temperature, they can be varied without changing the number of phases. Why F is equals to 2 now for one phase? Remember that we have one component. When we have one component, automatically our equation becomes 3 minus P. So if we only have one phase, which means from that equation 3 minus P, now it will be 3 minus 1. 3 minus 1, which is equals to 2. Hence, F is equal to 2. But the most important thing, where we have one phase, it means that the pressure and the temperature, they can be varied without changing the number of phases. So when 2 phases are present, 2 phases are now present. So it means that F is equals to 1. So this implies that the pressure is not freely variable if the pressure is set. This is why at a given temperature, a liquid has a characteristics of a vapor pressure. So in this case, as you can see, 2 phases, F is equals to 1. So if it's equals to 1, it means that at a certain temperature, here they're making an example of a liquid. It can also exist as a liquid, and it can also possess some characteristics of a gas. So what about when we have 3 phases? So when we have 3 phases, it means F is equals to 0. So this special case occurs at the definite temperature and pressure, that is characteristics of the substance. So normally, like in our graph, we normally say it occurs at the triple point. So at the triple point is whereby when you look at your solid phase, your liquid phase, and your gaseous phase, they are at equilibrium. Remember, if they are at equilibrium, it means that it is impossible for us to be able to differentiate between one phase. So in a nutshell, when I try to summarize this particular slide, it means that for one component system, remember that F is equals to 3 minus P. And for one component system, we can have various scenarios where we have one phase is present, the second one, 2 phases are present, And the last one, 3 phases are present. As you can see, even the values there, F is equals to 2, F is equals to 1, and F is equals to 0 respectively. So let's look at a typical graph for a typical graph phase whereby we are going to apply the phase rule. So this graph, normally they're the graph of pressure versus temperature. So in this case, we are going to increase the temperature, and we want to see what will happen with our pressure. As you can see from this particular diagram, so when we increase the temperature, what happened with pressure, we can see that the pressure, it is also increasing until the triple point. And beyond the triple point, when we increase our temperature, we can see that our pressure seems as if it is decreasing. Okay, from this graph, from this particular graph, we can have the region whereby F is equals to 1, a region where F is equals to 2, and we can also have a point or region where F is equals to 0. When F is equals to 1, it means that the two faces are in equilibrium. When F is equals to 2, it means that we only have one phase. And when F is equals to 0, it means that 3 phases are in equilibrium. I think in the next graph, maybe we'll look at a specific graph for a specific compound or an ion. So in this slide, they're just trying to prove the phase rule. Remember that we said that the phase rule is C minus P plus 2. So I think we can also go through your textbook and see how this thing it can be proven. So in summary, before I look at the typical example for a compound of an ion, for one component system, at most we can have 3 phases. One component system, 3 phases. Remember that F, which is the variance, it is equals to C minus P plus 2. When C is equals to 1, it means that F, it will be equals to 3 minus P. 3 minus P. Remember that for the phases, we said that we can have 1 phase, we can have 2 phases, and we can also have 3 phases. So if 1 phase is present, we said that F is equals to 2. And it means that pressure and the temperature can be varied independently. And we said that if 2 phases are present, it means F is equals to 1. And only pressure or temperature can be varied independently. And if P is equals to 3, it means that F is equals to 0. Remember I said that this one, it occurs at a specified temperature and pressure. And it occurs at a point that we call it the triple point. So let's look at a typical example of a single component. So in this graph, this is a typical example of a phase diagram for water. So from this graph, we have a number of points, as you can see. Point A, point B, point C, as well as point D. And we also have the triple point. So at point A, for water, that is where we only have the vapor that is present. As you can see that if maybe in this graph we have started with the solid water in a solid form, if we keep on increasing the temperature, obviously we'll end up with the water which is in the gaseous form, or as vapor. Hence at point A, the only phase that is present is the vapor. And we also have point B. Point B is whereby the liquid it boils, but vapor and liquid they coexist along the line, the vapor pressure curve. So in this instance, as you can see, So along that particular line, that is whereby vapor and liquid, they coexist. And we also have point C. So at point C, the liquid freezes. The liquid freezes. So below that point C, I think we also have the triple point. And the triple point, three phases, they coexist in equilibrium. And the last point is point D, and only solid occurs. So just to summarize this graph, let's say we have water in a liquid, in a solid form. So when we increase the temperature, we want to see what's going to happen with our pressure. I think from that summary, we have seen that when we increase the temperature of your water in a solid form, we'll end up converting that particular water into a gaseous form. So, but along those conventions, there are a number of scenarios that are going to occur. Like, for example, water will change from the solid form into the liquid form, and our water will also change from the liquid form into the vapor form. And from there, we'll also have the triple point. I think, good people, for this lecture, that is all for the single component for the phase diagram. So let us not forget like how to calculate P. But P, you only have to look at your reaction and you'll be able to identify which substances are given in liquid, solid, or in the gaseous form. And also how to calculate the number of components of the system. So during the previous lecture, I've made a number of examples how to calculate the component. Again, the other thing that is important, like the relationship between the number of phases as well as the number of components, which is given by the variance. And variance F is equals to C minus P plus 2. So for our lecture for today, I think we only spoke about the single component. Even for the single component, we can have F is equals to, we can have P is equals to 1, we can have P is equals to 2, and we can also have P is equals to 3. And for all those systems, we're going to have three various systems, whereby F it can be equals to 1, or F it can be equals to 2, or F it can be equals to 0. And when F is equals to 0, it means that the liquid, the gaseous, as well as the solid state, they are all in equilibrium. Thank you, ladies and gentlemen.